Okay, folks, this is a quick video, hopefully quick, on solving higher order linear homogeneous where the right side of the equation is zero, ordinary differential equations with constant coefficients. Recall first orders like ay prime plus by is equal to zero, where we would divide the whole equation by a, b over a y is equal to zero, then y prime equals negative b over a y. And you know the solution to this. It's a e to the negative b over a t or x, however that would work out. And it turns out solving higher orders, for example, like a y double prime plus b y prime plus c y is equal to zero works out similarly. So just like the solution for the first order differential equation here was an ae to the negative b over at. Let's kind of, I'm not going to use the word guess, but let's try y equals a now let's just do y equals e to the mt as a solution. If we do that, then our derivatives, we would get a, and then, well, let's do the derivatives real quick, because if we're going to plug these in and see if this works as a solution, maybe it will work. And you're going to see that it will, but it helps us figure out what the solution will actually be. So if y is e to the mt, y prime is m e to the mt, and y double prime is m squared e to the mt. Then, okay, then we'd have a m squared e to the mt plus b m e to the mt plus c e to the mt is equal to zero. Then let's factor out an e to the mt. We'd be left with am squared plus bm plus c is equal to zero. And if we're going to solve this, either e to the mt is equal to zero, or this quadratic is equal to zero, that polynomial. This exponential never has a solution, no solution ever, because e to the mt is always bigger than zero. So it couldn't be equal, but this other one, this piece, we can solve that. And m, let's see, m then will be plus or minus, no, it'll be negative b plus or minus square root b squared minus 4ac all over 2a. All right, so this am squared plus bm plus c equals zero is called our characteristic equation, because it's going to inform what our solution looks like. The characteristic equation will always have two roots. Equation will always have two roots. Always have two roots. And the roots, like we just mentioned, negative b plus or minus square root b squared minus 4ac all over 2a. And since our equation was a second order differential equation with constant coefficients, we know that a general solution will need two terms, general solution, because we'll have two terms because the differential equation was second order, and we just got finished talking about the last couple days how if you have a second order differential equation, the general solution will have that many terms, two linearly independent terms from a fundamental set, and general solution will have two terms because the DE was second order. Let's see. Let's write it like this. And the general solution will have two terms. Okay. The general solution is y is equal to some constant C1 e to the m1t plus C2 e to the m2t, where m1 and m2 were the roots of that characteristic equation. And depending on what roots you have, that then changes what your general solution can look like. In general, your solution is going to look like this, but depending on what kind of roots you have, that is going to determine what your general solution actually looks like. So let's look at those three cases, and we'll look at an example. All right, so we just finished saying that to solve the second order differential equation with those constant coefficients, homogeneous equation, the right side is 0. It boils down to solving this characteristic equation. This thing here is just a characteristic polynomial, and tells us our general solution will look like this: C1 e to the m1t plus C2 e to the m2t, where each of these, they're together linearly independent. And because of how quadratics work, this these roots come in three different types based on the sign of the discriminant, the b squared minus 4ac. So if the thing inside the root, the discriminant, is positive, then we're going to get two unique real roots. The m1 and m2 root will be not the same, and your general solution will look like this. So if you're going to solve 2y double prime minus 5y prime minus 3y is equal to 0, you find your characteristic equation, and that is 2m squared minus 5m minus 3 is equal to 0. We're going to factor that to find our roots, and that would factor into a 2m plus 1 and an m minus 3. This tells us that m is negative 1/2 and m is 3. So let's call that 1 and this 2. We get our two distinct real roots. So the general solution then is, and general solution is y equals C1 e to the negative 1/2 t plus C2 e to the 3t. That's it. You're done. The only way you get C1 and C2 is if you had an initial condition to come back and recover those things. So that's your solving process, and it's not that bad compared to what you've done before. So now let's look at b squared minus 4ac is equal to 0. That's telling you, if you were solving m is equal to negative b plus or minus square root, and then all the stuff on the inside is equal to 0 over 2a, then our m will equal negative b over 2a. And we get a repeated root in this situation. So both of our roots, we get two roots, they're the same. It's a repeated real root, and it's negative b over 2a. In that case, your general solution is a C1 e to the m1t and a C2t e to the m2t. And you have to have that extra t, again, because m1 and m2 are the same. And without the extra t, then these two terms would be linearly dependent, and we need them to be independent to form the general solution. So another example, let's factor the y double prime minus 10y plus 25y. Our characteristic equation would be m squared minus 10m plus 25 is equal to 0. That's going to be m minus 5 squared is equal to 0. M is equal to plus 5. And there's your repeated real root. So the general solution is y is equal to c1e to the 5t plus c2 t e to the 5t. Hopefully you can tell there, if we took out that t, then these two terms would be linearly dependent because they are the same. And we can't have that, so we need to throw in an extra t for the general solution. Okay, the last one, more complicated, but not bad. If your discriminant is less than 0, then the thing inside of the root is negative. You get complex roots. You get two of them, alpha plus or minus beta I. They're complex conjugates. We've looked at that before. Since they're distinct and different, your general solution would look like this with complex exponents, but that is usually, not accepted. So we use Euler's formula. E to the I theta is cosine theta plus I sine theta. And if you take this and apply Euler's formula, you get this as a general solution. And this uses real exponents in the alpha. As far as how that works out, we can talk about it later, but there's a file in your OneDrive for complex solutions. If you click that, then I'll just show you real quick. This explains, let's see, it's page 1 of 4. This is explaining how Euler's formula works out to give you that. And I have some examples in there. Euler's formula gives you the general solution with the real exponent. You don't have to know how to do that, but that's how it works out. Then let's look at an example and then we'll be done. All right, last one. Let's solve y double prime plus 16y is equal to 0. Your characteristic equation would be m squared plus 16 is equal to 0. This gives us m is equal to plus 0. 0 plus or minus 4i. That tells us alpha is 0 and beta, we're going to use the plus version, only not the minus version. Again, read that thing on complex solutions. Beta is 4. So your general solution is y equals e to the alpha t, so 0t, c1 cosine 4t plus c2 sine 4t. And the e to the 0t is 1, so you really don't need that, and you end up with c1 cosine 4t plus c2 sine 4t. That would be your general solution. Again, you'd recover c1 and c2 if you had initial conditions. All right, y'all. Please reach out with any questions, and we will hopefully talk soon. Bye.